In this lesson, you're going to learn about the second type of product we can do between two vectors. We can find the cross product of two vectors. So at this point in the course, hopefully you're familiar with dot product, sometimes called scalar product. Dot product only gives you a scalar result. Cross product, on the other hand, gives you a vector result. So sometimes cross product is called a vector product. This is the notation that means cross product. So if you see a multiplication symbol between two vectors, you have to understand that that means the cross product of the two vectors, and we would read this as A cross B. There are two different formulas for cross product, depending on whether we have geometric or algebraic vectors. The formulas may look a little bit complex, but by the end of this lesson, you'll understand what all of these variables in these formulas represent, and you'll understand how to calculate cross products, and more importantly, you'll understand what the results tell you. So when you're ready to get started, make sure you get a blank copy of the lesson from jensenmath.ca. You can find it in the Calculus and Vectors section. We are in the second vectors unit, and this is lesson 5, cross product. So you can get a blank copy of the lesson here, and after the lesson you can try the practice problems by clicking on worksheet. And don't forget, you can always check your work by clicking on worksheet solutions when you're done the practice problems. So let's get started. Let's start off by figuring out what the cross product of two vectors actually is. So I'm going to be referencing this diagram on the right over here throughout this portion of the lesson. Notice I have drawn here two vectors, vector A and vector B. The cross product of those two vectors is either this vector here, A cross B, or this vector here, B cross A. What's important to notice about those two vectors is both of those vectors, let's focus in on this one, A cross B, is perpendicular, or normal to, both vector A and vector B. That cross product vector A cross B forms a 90-degree angle with vector A, and also forms a 90-degree angle with vector B. So we say it is normal to vectors A and B because it is perpendicular to both of them. Same with vector B cross A. This one down here is also perpendicular to both of vectors A and vector B. So the first main property of a cross product we should understand now is the cross product of two vectors A and B in 3 space is the vector that is perpendicular to both of those vectors A and B, such that the vectors A, B, and A cross B form a right-handed system. Since A cross B and B cross A are both perpendicular to A and B, how do we know which direction our cross product is going in? We have to use this thing called a right-handed system to figure out that A cross B goes in that direction, and B cross A goes in that direction. So what is the right-handed system? The right-handed system tells you if you're trying to do A cross B, you would place your hand along vector A with your fingers pointing in the same direction as vector A, and then try and curl your fingers towards vector B. While doing that, your thumb will point in the direction of A cross B. So if you were to imagine your hand laying along vector A and then curling your fingers towards vector B, your thumb would have to be pointing in that direction. So that would be the direction of A cross B. If, however, we were doing B cross A, you would lay your hand along vector B and then try and curl your fingers towards vector A. To do that, you'd have to flip your hand almost upside down, and then your thumb would be pointing in this direction. So hopefully now you understand that the cross product of two vectors is a vector that is perpendicular to both of the original vectors. And hopefully you also now understand the right-handed system and how it can tell you what direction that perpendicular vector is going in. Sometimes you'll hear a cross product being described as into or out of the page. So for these two vectors, based on their orientation, if we were to be doing A cross B, we would place our hand along vector A with our fingers pointing in the same direction as vector A, and then we would try and curl our fingers towards vector B. To do that, if you were actually imagining your hand being on this page, your thumb would be pointing out of the page. It would be pointing straight up from the page. So in this case, based on this orientation, we would say that A cross B is out of the page. Alternatively, if we were to do B cross A, we would lay our hand along vector B and then try and curl our fingers towards vector A. And to do that, we would have to flip our hand over and our thumb would be pushing right into the page. So we would describe B cross A as into the page. So that's just another way of describing the direction of a cross product vector. Here's just a little bit of a 3D demonstration in GeoGebra. Notice I have my vector A and my vector B. If I were to do the cross product of these two vectors, I could do A cross B or B cross A. If I did A cross B, the direction of that vector, since here's vector A, if I tried to curl my fingers towards vector B, my thumb would be pointing in that direction. So A cross B looks like this. That's A cross B, right there. B cross A, on the other hand, if you laid your hand along B and tried to curl your fingers towards A, you'd have to flip your hand upside down and your thumb would be pointing down this way. So B cross A looks like this. Notice both of those vectors are perpendicular to the plane that vector A and B both fall in. So these two vectors are both perpendicular to both vector A and vector B. So cross product vectors are perpendicular or normal to both of the original vectors. Okay, we're going to start with the cross product of geometric vectors. And this is the formula for the cross product of geometric vectors. It's made up of two components: the magnitude of the cross product and the direction of the cross product. Cross product gives us a vector, so we need those two components. We need the magnitude and the direction. To find the magnitude of the cross product, we do magnitude of A times magnitude of B times sine theta. And to get the direction of the cross product of geometric vectors, we multiply it by a normal vector of length 1. So that's indicated by this symbol right here. This symbol is a unit vector perpendicular to both A and B. So when you hear the word normal, think perpendicular. And I should also mention that theta is the angle between the vectors when they're tail to tail. Before I actually go ahead and do an example 1, where I calculate a cross product between two vectors, I skipped over this page of properties about the cross product of vectors, and it would be useful for me to go over these quickly with you. So the first property, this is an important one, and you probably already noticed this when I showed you that demonstration in GeoGebra, but U cross V and V cross U are opposites of each other. This is what it's saying. U cross V equals negative V cross U. Let's look back at that diagram in GeoGebra again. Notice A cross B, B cross A, exact same magnitude, they're just pointing in the exact opposite directions. They're opposite vectors. Both of these cross product vectors are perpendicular to vector A and vector B. They're just pointing in opposite directions, so they're opposite vectors. The next couple properties are just telling you that distributive property holds true for cross product. So in a lot of ways we can treat cross product like multiplication. So U cross vector V plus vector W, you could distribute the vector U to the vector V and the W and get U cross V plus U cross W. Another property on here that shows you another way that cross product is treated like multiplication is that a scalar times vector U cross V would be equal to doing that scalar times vector U and then crossing it with V, or multiplying the scalar by vector V and then crossing it with U. Same way if, let's say, we had 2 times 3 times 6. We could do 3 times 6 first and then multiply it by 2, or do 2 times 3 first and then multiply it by 6. It wouldn't matter. So in a lot of ways, the algebra rules for doing cross product are similar to the algebra rules of multiplication. But cross product is not just multiplication. It gives us a very specific result. And the magnitude of the cross product actually gives us something very interesting. The magnitude of a cross product is equal to the area of a parallelogram defined by the two vectors. So the magnitude of U cross V equals the area of the parallelogram formed by vector U and V. Let me demonstrate this to you. Here, I've got two vectors, vector U, vector V. Let me first start by forming a parallelogram with these vectors. Oh, and I should also add in, if we're doing cross product, right, we know this angle between the two vectors when they're tail to tail. And if I wanted the area of this parallelogram, well, what's the formula for area of a parallelogram? It's just base times height. So I would have to multiply the length of this side, which is whatever the magnitude of vector U is, multiplied by the height. And the height could be represented with that dotted line there, where it's perpendicular to vector U. I could come up with an expression for the height of this parallelogram if I looked at this right triangle right here. In that right triangle, I'm looking to get an expression for height, I know the magnitude of that side, and I know this angle. So using a sine ratio from the reference angle, it would equal the opposite side, the height, divided by the magnitude of the hypotenuse, the magnitude of vector v. And then I would multiply both sides by the magnitude of vector v so that I could isolate the height, and I get an expression for the height. It's equal to the magnitude of v times sine theta. So the formula for area of this parallelogram formed by vector u and v is equal to magnitude of u times magnitude of v times sine theta. And if we look back to the cross product formula, that's this part right here, which I told you is the magnitude of the cross product. So magnitude of cross product gives you area of the parallelogram formed by those two vectors. Now that we know some interesting things about cross product and what it represents, let's see if we can calculate some cross products. Okay, let's do an example now. Example 1 gives us two vectors, vector u and v, and it gives us their magnitudes. Magnitude of u is 30, magnitude of v is 20, and it tells us the angle between them is 40 degrees. And the vectors are specifically in that orientation that it gives us, and they're in the plane of the page. We want to find two things, u cross v and v cross u. Remember, when doing cross product, you get a vector, and specifically a vector that is perpendicular to both vector u and vector v. So u cross v and v cross u are both going to give vectors that are perpendicular to these two, but they're going to be in opposite directions. So when we figure out these cross products, we're going to get both a magnitude and a direction. So the formula for u cross v that we just learned, it's equal to the magnitude of u times the magnitude of v times sine theta. That's the magnitude of the cross product. And then we also need the direction. It's multiplied by unit vector n. That means a vector of length 1 that is perpendicular to both of those. So this is the magnitude, and by multiplying it by that vector there, we're not changing its magnitude, we're only giving it a direction that is perpendicular to both u and v. And we can describe that direction as either into or out of the page. So for this one, u cross v, if we laid our hands along vector u, and then tried to curl our fingers towards vector v, your thumb would be pointing out of the page. When that's the case, we leave the unit vector as a positive value. If it was going into the page, we would make this negative unit vector n. Going into the page, we consider negative. That just puts it in the opposite direction, but still perpendicular. So for part A, we can leave it as positive unit vector n. And now we can sub into this formula. The magnitude of u is 30. The magnitude of v is 20. The angle between them is 40. And that's being multiplied by unit vector n. If I simplify the magnitude, I could get an approximate value for that from my calculator. So the cross product u cross v would be 385.7 times unit vector n. So that's a vector that's perpendicular to u and v with a magnitude of 385.7. And another way of describing the direction of this, instead of writing it as positive unit vector n, we could say out of the page. So we could say u cross v is 385.7 out of the page. If we were to start v cross u from the beginning, the formula would look exactly the same. It would be magnitude of v times magnitude of u times sine of the angle between them. But the unit vector we multiply them by, since v cross u, if we use the right-hand rule, I would have to lay my hand along v and then try and curl my fingers towards u. I would have to flip my hand upside down to do that, and my thumb would be pushing into the page. So instead of multiplying by unit vector n, I would need to multiply this whole magnitude by negative unit vector n. So if you're going into the page, we indicate that with the negative in front of the unit vector n. Remember, n stands for normal, perpendicular. So what we've done is we've taken the magnitude of the cross product, which is going to be the same as the cross product above. U cross v and v cross u have the same magnitude. They're both 385.7. And I've given it a direction perpendicular to both u and v. But this time, v cross u is in the opposite direction of u cross v. It's still perpendicular, but it's in the opposite direction. That's why I need the negative. So we choose for, if it's into the page, negative unit vector n. If it's out of the page, positive unit vector n. So when I simplify this, I get negative 385.7 times unit vector n. So that's the exact opposite of this vector. U cross v and v cross u are opposites of each other. Another way of describing this answer would be 385.7 into the page. Okay, so that's all we'll do with geometric vectors, and now move on to algebraic vectors. Okay, let's move on to part 3, where we do cross product of algebraic vectors. So remember, algebraic vectors are written in this notation. So we're working in 3 space, so for algebraic vectors, you'll see 3 components, an x, a y, and a z component. And for algebraic vectors, the tail is at the origin and the tip is at the point defined by those 3 coordinates. Now for this formula down here for the cross product of algebraic vectors, you'll notice I'm using this notation that has subscript 1, 2, and 3's. Just notice that a subscript 1 means the x component of the vector, a subscript 2 means the y component, and a subscript 3 means the z component. I just decided to use 1, 2, and 3 for this formula. Now this formula, it gives us a vector, right? Cross product is the vector product, it gives us a vector. And the formula may look somewhat confusing, but let me show you a little way we can set up the cross product of algebraic vectors so that we can generate these components of the vector, the x, the y, and the z components of that vector relatively easily. So if I want the cross product of vector a and b, what I need to do is set up 2 columns. One column has components from vector a, and one column has components from vector b. The way I set up the first column for components of vector a is I do the second component of vector a first, then the third component, then the first component, and then I write the second component again. And then the column for vector b, I follow the same pattern. Second component, third component, first component, second component. And I do this so that I can generate the formula for the cross product. The cross product, a cross b, is equal to, I'm going to get 3 components, an x, a y, and a z component. I can get the x component by doing the product of those 2 components minus the product of those 2 components. That will give me the x component of the cross product. So a2 times b3 minus a3 times b2. So that will give me the x component of a cross b. To get the y component, I do the product of those 2 minus the product of those 2, and that gives me the y component. a3b1 minus a1b3. And lastly, to get the z component, I do the product of those 2 minus the product of those 2, and that gives me the z component of the cross product. a1b2 minus a2b1. So this is the formula for the cross product of a and b. But we don't have to memorize that formula. We just have to memorize how to set it up and do all of the arithmetic. Example 2. Let's find p cross q, where we're given vector p and vector q as algebraic vectors. And each of those algebraic vectors have 3 components, an x, a y, and a z component. If I want p cross q, I know my result is going to be a vector. So I'm going to get an x, y, and z component for the cross product. I can get those components if I follow that pattern we just looked at when we created the formula for the cross product of algebraic vectors. I'm going to start by listing the components of vector p underneath of it, but by following the pattern where I always do the second component, then the third component, then the first component, and then write the second component again. So it would look like 3, 2, -1, 3. Now let me look at vector q. So underneath vector q, I'm going to list the components of it as well. And I'm going to follow the same pattern. Second component, third component, first component, and then second component again. So -5, 6, 2, -5. And now I can get the x component of the cross product by doing that product minus that product. So 18 minus 2 times -5 is -10. This will give me the x component of the cross product p cross q. Now I can get the y component by doing that product minus that product. So 2 times 2 is 4 minus -1 times 6 is -6. And lastly, I can get the z component of the cross product by doing that product minus that product. So 5 minus 6. So now I can simplify each of those components. 18 plus 10 is 28, 4 plus 6 is 10, and 5 minus 6 is -1. So this is the cross product, P cross Q. Part B asks us to find Q cross P. So we're working with the same vectors, so let me just copy and paste them over. And this time I want to find Q cross P. Well, I know it's just going to be the opposite of P cross Q, so technically I could just multiply this by -1, and that would be the fastest way to do this. But just for practice, let's do this the long way. Let's pretend we didn't know what P cross Q was, and let's do Q cross P. So if we're doing Q cross P, I list the components of Q underneath vector Q. So, and we list it in the order of second component, third component, first component, second component. So -5, 6, 2, -5. And now we'll do the same thing for vector P. We'll list second, third, first, second. 3, 2, -1, 3. And then to get Q cross P, I will get 3 components. The x component comes from that product minus that product, so -10 minus 18. The y component comes from that product minus that product, so -6 minus 4. And the z component comes from that product minus that product, so 6 minus 5. So Q cross P is equal to -28, -10, 1. The exact opposite of what we got here, right? We could have just multiplied that by -1 and got this one. Example 3 asks us to determine the area of the parallelogram defined by vectors u and v. Well, hopefully you remember that the area of the parallelogram is equal to the magnitude of the cross product of the vectors. So let's start by finding what u cross v is. Now it doesn't matter whether we do u cross v or v cross u here, because we're just finding its magnitude, so the direction doesn't actually matter. So when we do u cross v, we're going to get a vector, and after we get that vector, we'll find its magnitude, and its magnitude will be the area of the parallelogram defined by those vectors. So let's list the components of vector u in the proper order. Second, third, first, second. So 5, 2, 4, 5. And then vector v, same thing. Second component, third component, first component, second component. 2, 7, 3, 2. And now to get the x component of u cross v, I do that product minus that product. 35 minus 4. To get the y component, I do 2 times 3 minus 4 times 7. So 6 minus 28. And to get the z component, I do 8 minus 15. That product minus that product. Let's simplify this. And I get 31, -22, -7. And if I want the area of the parallelogram, the area would equal the magnitude of u cross v. So to get the magnitude of the vector, we use the formula for magnitude, which would equal the square root of the sum of the squares of each of the components. So the square root of 31 squared plus -22 squared plus -7 squared. So that equals the square root of 1494 units squared, or approximately 38.65 units square. Part B of the same question asks us to find the angle between vectors u and v. So the best way to actually do this question is to use the rearranged dot product formula. But since we're in the cross product lesson, let's use cross product to figure it out. So remember, the cross product formula is equal to magnitude of u times magnitude of v sine theta multiplied by its direction. So remember, in this cross product formula, this part right here is the magnitude. So I could write a formula for the magnitude of u cross v without that unit vector n. And now I could isolate sine theta by dividing both sides by magnitude of u times magnitude of v. And I now have a formula where sine theta is isolated. So I could find the angle by doing inverse sine of whatever that ratio is. And we actually already have the magnitude of u cross v, so we could sub in for that. It was root 1494. And now let's find magnitude of u and magnitude of v. So I just quickly wrote a reminder of what vector u and v were. So magnitude of vector u would equal the square root of 4 squared plus 5 squared plus 2 squared. And the magnitude of v would equal the square root of 3 squared plus 2 squared plus 7 squared. Let's simplify this. This simplifies to root 45, and this simplifies to root 62. And this is what sine theta is equal to. We actually encounter a tiny bit of a problem here though, because we have a positive sine ratio, and we're looking for an angle between the vectors. Remember that there are two possible angles between 0 and 180, where sine is positive. So when we evaluate this, when we solve for theta by doing inverse sine of this, we're going to get this answer. I'll call this theta 1. But how do we know it's not theta 2? How do we know it's not the angle over here in this quadrant that would have the exact same sine ratio? The answer is we wouldn't know which one. That's why it's called the ambiguous case of sine. We wouldn't know which angle it actually is. So by using this formula to find the angle, we don't know which of the two angles it is, so we would have to state both of them as possible angles for theta. So when I do inverse sine of this ratio, I'll get theta 1, and I get about 47.03 degrees. That's the angle here. But this is also a possible angle. I have to consider in the ambiguous case of sine for this question. So theta 2, there's another possible angle. I would do 180 minus the reference angle here, which is 47.03. And I would get about 132.97 degrees. So both of these are possibilities. We don't know which one it is. It could be either or. So when using rearranged cross product, we actually have to consider the ambiguous case of sine, and we get two possible answers, and we don't know which of the two answers is right for the angle between the two vectors. To figure out which one of the two is right, we have a couple options. We could actually graph vector u and v and then just look and see which angle does it look like. We should be able to tell the difference between a 47 degree angle and a 133 degree angle. Or, algebraically, we could have done rearranged dot product, and we could have solved for the correct angle. Because dot product involves cosine, not sine, and there's only one angle for a cosine ratio between 0 and 180. So let me just graph these two vectors in GeoGebra quickly, and we can figure out which of the two angles is correct. Okay, here's vector u and v. The angle between those two vectors is clearly an acute angle. So after inspection in GeoGebra, we know that this is the correct answer for the angle between them. But without graphing them, we wouldn't have known that. So from this example, just a good takeaway would be when finding an angle between vectors, don't do rearranged cross product. Don't use this formula. Use the rearranged dot product formula instead. Alright, so that's it for this lesson. I hope you now know what cross product is and how to calculate it.